In this section, I'll show you how to obtain internal forces in structure members. Using this beam structure as an example, the objective of this section is to obtain all the internal forces developed in the structures due to the given sets of external loads. So if you take a cross-sections of any locations, you will find three different forces acting on them. First is the axial force N, and the shear force V, and the bending moment M. So we need to be able to obtain these forces at any locations of the structure, as well as represented them through a graphical ways, which is shear force and bending moment diagrams. So before we begin, we need to define the sign convention for these forces. So shear force is defined as positive if it's acting on the left-hand side of the surface pointing upward. It's defined as negative on the left-hand side of the surface is pointing downward. On the right-hand side of the surface, the shear force is defined as positive, is pointing downward, and pointing upward on the right-hand side of the surface is defined as negative. Now, bending moments on the left surface is defined as positive if it's doing clockwise. On the right surface, is defined as positive if it's doing counterclockwise. We also need to follow a coordinate system, so we use this coordinate system. X is going from left to right, while Y is pointing upward. So how do we relate internal forces to external forces? So we can take a small elements out of the structures. So the small elements is described by the width of dx, and putting all the forces on it, shear force, bending moments, and external distributed force, W. The result of the distributed force is to cause the change of the shear force and bending moment on the right surface of the elements. Now, to relate all these relationships together, we can use equilibriums. So we use summation Fy, vertical directions, to set up the first equations, and then summation moments on the left surface of the elements to set up the second equation. So if you do rearrangements and ignore the higher order terms, then this is what you will get. Two equations. The first equations show you dV over dx is equal to W, and the second equation is dm over dx is equal to V. Physically, it tells you that the slope of the shear force is equal to the magnitude of the distributed force, while the slope of the bending moment is equal to the magnitude of the shear force. So how do we use these two equations? Now we can use these two equations through integration very quickly. For instance, if I'm interested to find out the differences at the two locations in terms of their shear force and bending moments, we can take these two equations and perform integrations. So the first equations tells you that the differences between the shear force at the two locations is equal to the integrations of the external force between the two locations. And the second equations similarly tells you that the differences of the bending moment is equal to the integrations of the shear force between the two locations. So with these two integration equations, it helps to establish the relationship between the shear force and bending moment at the two locations. How about concentrate force and concentrate moments? So we can go back to the elements and take a look at the effects of the concentrate force first. So you can see that based on force equilibriums, if I have a concentrated force applied on the elements, the result of this concentrated force is to cause the shear force on the right-hand side of the surface to reduce by the magnitude of that concentrate force. So graphically, you can see that the result is the shear force is going to have a shear force jumped with a magnitude of P right at the loading location. Similarly, for concentrated moments, the effects of the concentrated moment is going to be reducing the moments on the right-hand side. So graphically, again, the results of the concentrated moment is to cause the moment jump at the moment diagrams. So let's put all these together and use a simply supported beam as an example. So I want to illustrate to you how we can use the equations to draw the shear force and bending moment diagrams. So here's the sign convention that we follow, and here is the coordinate system that we use. So based on equilibriums, we can find out the reaction force at the two support, which is equal to P over 2. And based on the results, we can immediately draw the shear force diagram, because this reaction force, according to our sign conventions, corresponding to a positive shear force of P over 2. And after that, you see that there's a regions that you don't see any external loads, which tell you that W is equal to 0, so indicating that the slope of the shear force is equal to 0. So that's why the shear force is equal to constant of P over 2 there. Then you see this concentrate force, as we mentioned, that the effects of the concentrate force is to cause a shear force jump. So the shear force is going to go through a jump downward of magnitude P. And beyond that, you don't see any loading again. So W is again equal to 0. So the slope of the shear force then again is equal to a constant of minus P over 2. So that's the shear force diagrams. Now, bending moment diagram, according to the equations, so the bending slope of the bending moment is equal to the shear force. So shear force is equal to P over 2 positive for this regions and minus P over 2 for this regions. So indicating that the slope of the bending moment will be equal to positive P over 2 for this regions and then negative P over 2 for that region. So after you obtain the bending moment diagrams, you can go to moment curvature equations, which is m over EI equal to curvature, and then draw the deflection shape. So if you have a positive bending moment, then the curvature should be positive, which will give you a convex shapes of deformations. If the bending moment is negative, then the curvature will be negative, then you should get a concave shape of deflections. So in this case, the bending moment is positive. So the deflection shape should be convex. So based on this information as well as the boundary conditions, then we can draw the deflected shape of the structure. Now, quite often, engineers would like to plot the bending moment at their tensile side. Now, in this case, the tensile side is corresponding to the bottom surface of the beam. So instead of plotting the bending moment like that, engineers usually like to plot the bending moment at their tensile side, like this. So the purpose of that is to remind the engineer themselves that they should put rebars at the bottom of the structures. So here's a summary of how you can get the shear force and bending moment diagrams. So it starts from structure under loads, and then you use dV over dx equal to W to construct shear force diagrams. And then you use dm over dx equal to shear force to construct moment diagrams. And then you use moment curvature equations, m over EI equal to curvature, to construct quantitative deflection shape. After that, you can redraw your bending moment diagram so that they are drawn at the tensile side of the structures. As you practice more and more, an experienced engineer will be able to draw the deflection shape straight from the structure under loadings. So this will also help you to double check the analysis results that you obtain. So here are the summaries of what we have discussed. So there are two cases here, concentrate force and concentrate moments. So here are the equations that you can use to construct shear force and bending moment diagrams. So on the first case, the shear force is VL on the left-hand side, bending moment is ML, and on the right-hand side is VR, and bending moment is MR. So you can draw the shear force diagrams, VL, and on the right-hand side is VR. So as we just discussed, there are no loading between VL and P, so the slope of the shear force should be equal to 0. And then you see a concentrated force P, so you see a shear force jump of P. And then you enter this no external force region again, so shear force is equal to 0. And based on this equation, it shows you that the slope of the bending moment should be equal to the shear force. So just pick up the shear force value there, and then use that as the slope of the bending moment. So we can have the similar approach for the concentrated moment. So if you look at the two equations closely, you will find out that mathematically it tells you that shear force is always one order higher than the external distributive force. So for instance, if the distributive force is 0, then shear force is a linear function, one order higher. If the distributive force is a linear function, then shear force should be a second order function. Similarly, moment is related to shear force through dm over dx equal to the shear force. So it tells you that the moment is one order higher than the shear force. So if the shear force is first order, then the bending moment will be second order. So using this as an example, this is a case that distributive force is a constant. So shear force will be one order higher than that, which is a first order. And bending moment will be a second order polynomial. The second case, the loading is a first order. So you see that the shear force become second order and bending moment then become third order.